Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about the loss of kinetic energy in an oblique impact with a fixed surface. Well, if we're talking about kinetic energy, we will directly be involved in calculations which implicate the elasticity of the collision. What do we know about elasticity? The coefficient of restitution, applied using Newton's restitution law, lies between 0 and 1. If E equals 0 and we were cricketers, we'd describe the wall as a pretty limp affair. It doesn't give any life back. On the other hand, if E equals 1, that will be a perfectly elastic collision, and in that case there will be no loss of kinetic energy. When we consider the change in kinetic energy, we'll do it by calculating the difference between the final and the initial kinetic energy. Though if we realize that if the initial kinetic energy is less than the final kinetic energy, that will implicate a loss, so sometimes we may do the difference the other way round. So there you are. If you have a negative answer, that indicates a loss. Right, what are we talking about? An oblique impact with a smooth plane. Now that means to say that when the impact takes place, the only force of interaction between the ball, or whatever it is, particle, and the wall can be perpendicular to the wall. So momentum will be conserved, well, the component of momentum parallel to the wall will be conserved. On the other hand, we can apply Newton's law of restitution along the perpendicular. So that's the picture. And for kinetic energy, we'll be interested in the particle's speed, though that will mean, of course, that we need to consider the components first. So here we are, an example shown in this picture. A 4 kilogram mass is incident with a velocity of 1.5 meters per squared, 1.5 meters per second, is incident with a smooth wall, a plane wall, and there's the picture which shows the setup. We'll need to bring in an expression for the velocity afterwards. Then we use restitution perpendicular to the wall. So first we need to calculate the component 4 cos 45, which is the component of the 4 perpendicular to the wall, and then we multiply it by 0.4 to get the new component perpendicular to the wall, and it will be in the opposite direction as is shown by the minus sign. Cos 45 is 1 over root 2, so that works out quite simply as 0.8 times root 2. Along the wall, momentum's conserved, so we simply need to work out the component parallel to the wall, that is 4 cos 45, and that will be the same afterwards, hence V2. So we're going to take those two numbers, the 0.8 root 2 and the 2 root 2, into the picture on the following page. There we are. So now we know the setup, we know the speed to start with, it's 4. We'll need to work out the speed to finish with if we're talking about kinetic energy. So that's done by the Pythagorean calculation, the square of each component added, and take the square root. You can just about do that in your head. 0.64 times 2, that's 1.28, plus 2 root 2 squared is 8, so the square root of 9.28. So now we move to calculating from the root 9.28 and the 4, the difference in the kinetic energy. It will be the half mv squared before and the half mv squared afterwards. So, and that is an example where I've done it in a sense in the wrong way round, because I expect to find a loss. So if we do those calculations the simplest way, it works out as 5.04. There's no need even for an approximation there. So finally the energy loss is 5.04 joules. That concludes this video presentation. The next one is on successive oblique impacts with plane surfaces.